Okay, so this is section 5.8 on inverse trig integration. So from the previous section, we have our 6 derivative rules for these inverse trig functions. So I've got them all kind of organized here. And if you'll notice, the cofunctions, like sine and cosine, tangent and cotangent, secant and cosecant, that their formulas, their derivative formulas, differ by just a negative sign. That's super helpful for us because what that means is when we start trying to pull this backwards using integration, and we look at these formulas and we're like, hey, if I just integrate this, I really only need 3 integration formulas for this. So that's going to be super awesome for us. So let's have a look at those 3 integration formulas. So we have this 1 over 1 minus x squared dx, which is arc sine x plus c. If there happened to be a negative, then we would just have that negative arc sine x plus c. 1 over 1 plus tangent squared is arctangent. And then 1 over x, square root of x squared minus 1 is the arcsecant of the absolute value of x. Now, what we can do is extend these formulas just a little bit further by using some substitution. So instead of being locked into just having, ones and x's, we can extend this a little bit more to having, a squared, some kind of other constant there, and some other function of x in there. So I put a little happy thought cloud over here saying that, hey, if you were to do a substitution here, that's kind of where that plays out. But these are the ones that are on your formula sheet. So we get this more general form instead of these much more specific forms. So this being any constant squared minus u squared du ends up being the arcsine of u over a. Now, if you were to differentiate this using our derivative formula from the last section and using the chain rule, you would get this after some algebraic simplification. So for this one, for the 1 over a squared plus u squared, that this ends up being 1 over a times arctangent u over a. And then this is the formula for that arcsecant. All right, so let's see how these formulas are going to go for us. Let me grab a piece of paper, cover up some of these answers as we go along. All right, so this first one, we have the integral of dx over the square root of 4 minus x squared. This one is very similar to that arcsine formula that we just had. And in that formula, we had that a squared minus u squared. So we can see that that 4 is my a squared, and my u, in this case, just happens to be x. So that formula is going to, if I put it into the same form as my formula, that's going to be that 1 over 2 squared minus x squared, that big square root there. Meaning that my a is 2. So using that formula, I get that this integrates to just be the arcsine of x over a plus c, where a is 2. So this is nice and highlighted in the notes that are posted. But because I'm having to re-record this video, my nice highlighted notes are still in my office and not at home. So I'm having to use a copy of them. So these aren't as nicely highlighted. All right. This next one, we're going to have to do a little more work to get it into a standard form that's on our formula sheet. This one's giving some arctangent vibes because it doesn't have a square root of any kind. So we get that this 2 over here is my a squared, and this 9x squared must be my u squared. So rewriting that, okay, so 2 is my a squared. That must mean that a is the square root of 2. Not pretty, but it's okay. Square root of 2 squared is just 2. And then 9x squared, if I rewrote that as u squared, where u is some function of x, that is 3x quantity squared. Now, to do this, I am going to have to do some substitution here because my formula is a squared plus u squared. I do need to let u be 3x so that my du is 3dx. I get this extra 3 in here that I don't have in my original integrand. So dividing both sides by that 1/3. So here's that 1/3 from right there. And then this becomes that du over a squared plus u squared. Now, using that integration formula, we get that here's my 1/3 along to the right. But this form right here integrates into 1 over a. In this case, a is root 2. Arctangent u over a plus c. I do need to go back and substitute back in for u, and I'm going to go ahead and combine these two into one thing. So I get that 1 over 3 root 2, arctangent 3x over root 2 plus c. Now, you know, having a square root in the denominator is not always pretty, so I could see, you know, the back of the book or Calc Chat wanting to rationalize that. So if you were to multiply by root 2 over root 2, that would rationalize into this. So both of those are perfectly acceptable answers. Now, it's not always pretty, but you can always check your answers by taking the derivative. So, you know, looking back at example 1a here, I integrated this dx over the square root of 4 minus x squared. I got arc sine x over 2 plus c. So if you wanted to go through and just check your work, then you can take the derivative of this arc sine of x over 2 plus c. Now, remember, x over 2 is the same as 1/2 x. So when I take that derivative, I'm going to have to use the derivative rules from the previous section. That's going to be the square root of 1 minus u squared times the derivative of u. So the derivative of this x over 2. The derivative of this x over 2, because it's a 1/2 x, that derivative is just 1/2. And then plus 0, that's the derivative of c. So I'm just going to do some simplifying here. That 1/2 I just put right here in the front. That's 1 over 2, square root of 1 minus x squared over 4. I just squared those out. Now we got to do a little bit of simplifying here. This is 1 minus this fraction x squared over 4. So I rewrote this 1 as 4 over 4. So I could pull that together into one fraction. So I made that 4 minus x squared over 4. So see, 4 over 4 is that 1 right there. In doing that, I can split this up into the square root of the top over the square root of the bottom. The square root of this 4 right here is 2. So that means that those 2's are going to cancel. So that square root of that 4 right there is that 2. And those 2's cancel, and boom, there we go. That was the integrand of the original. So, you know, if you have some extra time and you want to check this using a derivative, you absolutely can. It's not always pretty, but, you know, it can be done. All right, so if we want to evaluate this one's given some arcsecant vibes here because of that outside x. In order to use that arcsecant formula, so the first thing I did was go ahead and rewrite this u squared minus a squared. So I rewrote this as a quantity squared, right? and this 9 as 3 squared. That's kind of a problem right here because I get this x out here and that's a 2x. Those need to be the same to use that arcsecant formula. All right, well, we can kind of get around this here. If I let u be 2x, all right, then my du is 2dx. I'm going to divide both sides by 1/2. This is a scan. Or sorry, a copy of my scanned notes, and it was a black and white copy. The color in my printer is out. So this 1/2 du over here is going to replace my dx. That's not the weird stuff. What's weird is that I'm going to take this u equals 2x and I'm going to solve it for x so that I get x equals u over 2. That is going to go right there. So I get this 1/2 out here. There's that du. I've got this u over 2 right there. And then, of course, I've got my normal u substitution happening. So here's a lot of stuff, a lot of substitution is happening here. Replacing the 2x with u. Dx, I'm replacing with 1/2 du. So there's my 1/2 du. This x out here was my problem, but what I did was take this and solve it for x by dividing both sides by 2, so I could replace that with u over 2. Now what that does, here I get a 1/2 here, and then here I've got another 1/2, but because it's on the bottom of that fraction, this is essentially yellow 1/2 divided by green 1/2, and those 1/2s cancel. So that ends up being pretty awesome because then I get something so much nicer, so much arcsecanty. So using my integration formula, so looking at it in this form, my a value is 3, so I get 1 over a, which in this case is 3, arcsecant, the absolute value of u over a plus c. And then I do have to resubstitute back in for u, which was my 2x. So the formulas that I keep referring to were the ones back here. So I'm constantly referring to these 3 that are on your formula sheet. So I'm constantly referring to those 3. And always trying to just manipulate it, either algebraically or doing some substitution into one of these 3 forms. That was example 2. Look at example 3. So we've got a natural log in here. So I don't know about you, but I'm looking at that natural log and I'm thinking, if I let u be that, my derivative is going to be a 1 over x. So maybe that x right here, you know, you think of that as 1 over x. That's actually kind of nice. So let's let u be that natural log. That du is going to be this 1 over x dx. That 4 is just going to be hanging out along for the ride. So you can see I just kind of moved that 4 out of the way. This x got absorbed into this 1 over x dx. So this really just became my du, and that's just 1 plus u squared. This 1 right here tells you that a squared is 1, which makes a, the value of a be 1. All right, so then going back to this formula right here, this integral is going to be 1 over a, arctangent u over a plus c. Okay, so 1 over a. Well, first of all, we got this constant multiple of 4. You'll notice that I didn't put a 1 over a because a is 1. I just didn't write 1 over 1 of arctangent u over 1. I just didn't write those ones in there since they didn't change anything. And I just substituted back in for u to get that natural log of x. All right, example 4. So the arc sine of x, quantity squared over 1 minus x squared. This one is really sneaky because you have to notice that the derivative of the arc sine is this 1 over the square root of 1 minus x squared. Now you may think, well, that's the whole daggum integral. It's not. We get that squared up there. So if we make this substitution, this bottom stuff and this dx all get absorbed into your du. That's just u squared. So look at that easy integral. It is nothing more than u squared, which is just u cubed over 3. Put that u back in. Boom. Right? That one's actually looks really nasty, but I mean, has a great personality, fun at parties, just really great. All right, next up, example 5. And I'm going kind of fast because you guys have the luxury of being able to replay this, pause it, things like that. Find the area under the curve of 4e to the x over 1 plus e to the 2x. And from x equals 0 to x equals ln root 3. That's just another way of saying that this is a definite integral. We got to be a little clever about this one because this e to the x and this is an e to the 2x. These aren't the same. So that's already kind of like making me cringe. But I can write e to the 2x as e to the x quantity squared. Because remember, if you have a power raised to a power, you multiply the exponents. So now here's the first substitution you might think to make. You might think, okay, I'm going to let u be this denominator. But look at what happens. The derivative of this is 0. The derivative of e to the 2x is e to the 2x times 2 dx. That's a 2x. That's not a 2x. So we've got ourselves an issue with that substitution. So I wrote that on purpose just to show you why that wasn't going to work. Just in case you tried that, you would look at that and say, oh, okay, that's why she didn't do it that way. So here's what we are going to do. I'm just going to let u be plain old e to the x. du, e to the x. And look at what happens. This becomes 1 plus u squared. The top becomes 4 du because my derivative of e to the x is e to the x. So this e to the x dx gets absorbed into my du. That's just a beautiful arctangent where my a value is 1. And this 4, that's just a constant multiple. I do need to substitute back in for u, which was my e to the x. And oh, yeah, this was a definite integral, so we need to keep going. So I am going to plug in ln root 3 for x and then 0 for x and subtract those. Now, before we start doing this, look, e to the natural log of something, that e and that natural log are inverse functions. They undo each other. That's nothing more than just root 3 right there. And e to the 0, that's just 1. So that already simplifies into something a lot nicer. Now, what is the arctangent of root 3? Well, that's the angle whose tangent is root 3. That's a 60-degree angle. The angle whose tangent is 1 is a 45. Getting a common denominator here of 12. So 1/3 minus 1/4 ends up being 1/12. And then multiplying by that 4 is going to give me a 1/3 pi. Grab the calculator in the drawer real quick. If you don't recall that kind of stuff from pre-calculus, here's what you can do. Let's put this in degree mode. Oops, got a little bit of a glare there. Put it in degree mode. And let's do the inverse tangent of the square root of 3. They give you 60 degrees. Now, the thing is, with calculus, we have to work in radians. But I feel like if you get this and you get 60 degrees, that you can maybe just say that you may be comfortable enough to say, oh, yep, that's pi over 3. And the inverse tangent of 1 is 45 degrees. And you might recognize that pretty quickly as being pi over 4. Okay. Moving on along, we have some of these that do not start off as nicely in these forms that we need. So we have to work a little harder to force this integrand into a form that we can use. Okay, so we're going to have to work a little harder on this. In this, we're going to have to complete the square in this denominator. All right. Now, what that means is that I'm going to take this denominator right here, that x squared minus 2x plus 2, and I'm going to leave a space right here. I'm going to add a number in so that this trinomial will factor into something times itself, better known as something squared. So essentially, what can we put right here that will make that thing into a square, that will complete this square? Now, this number is not something that you just have to randomly pull out of your butt. There's actually kind of a process that we can use to find it. And it's if you take this middle coefficient here, and I say middle because I know I'm going to have a third term in here. Take this x coefficient. Take half of that number and then square it. So half of 2 is 1. 1 squared is 1. So I put a plus 1 right there. Now, here's the thing. I'm not looking to change this expression. I'm just looking to tweak it, okay? I'm just looking to throw some lipstick and a dress on it. So I get this plus 1 right here. I've got to offset it with that minus 1. So what that means is that if I were to combine these like terms, I would get this exact same expression. This expression is exactly the same as this one. I'm just making this one look different. Okay. Now, inside this parentheses, inside there, that will factor into x minus 1, or x minus 1 quantity squared. This right here, this positive 2 minus 1 is a plus 1. So now all this kind of side work that I did, going back to this yellow stuff, that is now how I'm going to write that yellow stuff. This, okay, now this is giving me some arctangent vibes, okay? Because I can take that 8, that constant multiple of 8 out of here, and then I get this 1 over u squared plus a squared kind of business, right? I swear, every time I hit record, my dog suddenly decides that she is a camel and she has to get a drink. And then she's got to, lick all the water off of her, and she's got to hork a few times and give me some slurping limbs. And ugh. Anyway, so if you hear that in the background, that's what's going on. It's not me slurping and horking. The, it's the jowly beads behind me. All right, so anyway, I'm going to let u be this x minus 1. So du is just 1 dx. And look at how pretty that is. Just that 1 over u squared plus 1. That means that this is my a value. Again, a is 1 because that's a squared. Not because that's a 1. It's because that is an a squared, and the square root of 1 happens to be 1. So going back and using that arctangent formula from back here. Boop. Remember, a is 1, so that's why I did not write 1 over 1, u over 1. So that's going to be this constant multiple of 8, arctangent u plus c, and substituting back in for u. So the rough part of this one is that completing the square. That's where things can get messy. So let's look at another one. This one is, keep pushing that out of the way. This one's really ugly. And it's not initially ugly. It kind of is like a slow burn. Like one of those insults that just kind of slowly hits you, and you realize later, you're like, oh man, that wasn't nice. And that's kind of what this one is. It looks innocent enough, but man, oh man, it is not. We cannot just let u be this bottom stuff, because then we'll just get a minus 2x, which we got this plus 2 in here. That's what's messing us up. Man, if it weren't for that plus 2, we could just do a straight up Calc 1 u substitution here. But it's that plus 2 that's messing with us. But check out what we can do. And that's what all these things are about. It's about having all this integration and just getting this bag of tricks so that you kind of know, okay, I'm going to try this. I'm going to try this. I'm going to try this. This technique right here is not usually something that's the first thing that you try, of splitting it up. This is like the White Castle of techniques for integration, right? This is not somewhere you go, it's somewhere you end up, right? Because you just tried some other stuff and you just kind of ended up here because other stuff didn't work. So, all right, I'm splitting this up into x over this denominator plus 2 over this same denominator. Now, I got this vertical line in here as a visual separation because I am doing 2 separate integrals. So let me just cover this one up. We'll come back for it later. Let's just look at this x over the square root of 4 minus x squared. This is a nice little Calc 1 integral, all right? We can let u be 4 minus x squared. Du is negative 2x. We got an extra negative 2. That's okay. We'll divide both sides by negative 2. So we got that negative 1/2 hanging out here. And this then reduces down to be 1 over the square root of u. I'm going to bring that square root up, make it a negative 1/2 power to make it more obvious that I'm going to use the power rule. And remember the power rule for integration, we're going to add 1. So that's going to be u to the 1/2 over 1/2 when I integrate it. So u to the 1/2 divided by 1/2. See what I'm doing here? Divided by 1/2 is the same as multiplying by its reciprocal. And this negative 1/2 is still carried along from that du business. So those 2's can cancel. I get negative, just square root of u, plugging back in for u. That side's done. And now we're at this side. That plus 2 over here that we didn't like. This, now, this has got some arc sine feel to it, where 4 is my a squared, so that means that a is 2. Oops, I wrote a squared is 2. a is 2. A squared is 4. And then my u is x. So I get this 2 that I just pulled to the outside to make it more obvious that it's an arc sine. There's my a value. There's my u value. I don't even need to do a substitution here because my u is just x. So I get just 2 arc sine x over a. So that a right there. This 2 is just from along for the right. And then just pulling those two answers together. I've got my answer from this first integral, and then I've got the answer for this integral, and I'm just going to throw one constant of integration at the end. I don't need 2 of them. If you just wanted to throw 2 of them on there, you can. Right. So let's do another one where we're going to have to evaluate this. We're going to evaluate this by completing the square. This is a messier completing the square. Right? So here's what I'm going to do. I'm going to do some side work. So this side work right here, I'm just going to take that stuff out from under that radical and just kind of deal with that temporarily. Right, so all of that stuff right here is all of my completing the square. So I'm just going to pull this guy out and just, deal with him separately. Before you can complete the square, one thing we have not had to contend with yet, that is that this leading coefficient must be a 1 in order for us to be able to do that nifty little taking half and squaring it trick. So I'm going to have to factor out a -1 from both of those. So I just factored out that negative right there. That became x squared plus 4x. Now I'm ready to complete the square. So this minus x squared plus 4x. So there's my minus x squared plus 4x. To complete the square, I'm going to take this 4 right here. Half of it is 2. 2 squared is 4. Boom. There's my number that completes the square. Now, remember how I said that we want to keep this the same expression as what it was before. So we have to compensate. So if we add 4 here, well, you might think, well, I would subtract 4 here. You would be right. However, that minus on the outside of these parentheses means that I really just added a -4. So to offset a -4, I need that +4. So what this means is if I were to take that negative and redistribute it and then combine my like terms, I would end up with exactly the same expression that I started with. So this is really tricky because of that negative on the outside. All right, let's factor what's inside those parentheses. Let's factor that trinomial. That's going to factor into x plus 2 times x plus 2, or x plus 2 quantity squared. Still got that pesky negative hanging out there. Now I've got that +4. Now all I did was take this and flip it around so that I didn't have that leading negative right there. I just rewrote it as 4 minus some quantity squared. All right, so going back to my original integral up here, I'm now going to replace pink stuff here with this pink stuff, which is the exact same thing. If I factored that out and then combined and distributed that minus and combined like terms, I would get this exact same pink stuff. But in this form, this completing the square form, it is much easier to integrate because then it fits a form that we know. So I'm going to let u be this x plus 2. du is dx. We can see here that my a is going to be 2 because that 4 is 2 squared. That's going to, so this form right here is going to integrate into arc sine u over a plus c. My a here is 2. And then substituting back in for u, that u was x plus 2. So we'll put that x plus 2 back in there. This was a messy completing the square because of that leading negative out here. If this had been like a 3 that I'd had to factor out, it would work the same way. I would just kind of have this messy 3, although that would make this so much worse. So we're not going to run into those. So, okay, one more. One more example. Let's do an E problem here. So we did one earlier that had an e to the 2x, where I had to think of it as e to the x quantity squared. So this one, very reminiscent of that. So it looks innocent enough. Kind of seems like, all right, cool, I'm just going to let u be e to the x, so du is e to the x. But here's where my problem comes in. I don't have another e to the x somewhere to absorb into my du. So that becomes problematic for us. So what am I going to do? Well, this is just kind of another trick. So I'm just showing you a whole bunch of different techniques. It's not something that I would have expected you to know to do without me having shown you this technique. I want you to take this du. We're going to divide both sides by e to the x. Very weird, right? To have the u's and the x's mixing it up together. But that's because e to the x, this e to the x right here, I replaced with that u right there because u is e to the x. So that extra e to the x that I did not have for my du, I divided both sides by e to the x and said, hey, you know what? I can replace this, get rid of that x, and still keep a u in there. So here's what this ends up being. Going back to my original integrand, remember I wrote e to the 2x as e to the x quantity squared minus 1. This makes my u into e to the x, and my du over u is going to replace this dx. So right here, this dx here is going to be that du over u. So what is that going to look like when that substitution is done? Well, I'm going to get 1 over the square root of u squared minus 1. There's my a squared. And then the dx becomes du over u. When I pull that together, that u, don't put that u under that radical. So instead, I just moved it in front of that radical, so there was no confusion that it was under the radical. And now, oh, okay, yeah. So I got that u right there. That's giving some arcsecant vibes. Remember right here, this is whispering some sweet nothings to you. It's telling you that a is 1. So that's going to be arcsecant, the absolute value of u plus c, and then substituting back in for u is e to the x. And, you know, technically, you know how sometimes you have those absolute values and then like randomly the answer won't have the absolute values. That's because e to the x is positive for all values of x. So you don't actually have to worry about having it in there. So, okay, so that does finish up section 5.8.